Hello, my name is Kendra Spires. Welcome to our next webinar. We are so happy for you to be joining us today. We're going to be talking about our dual stream H2S analyzer, when you should use it, where you should use it, the measurements Envent can provide on a dual stream analyzer. We're going to walk through the principle of operation, and then at the end we're going to actually walk through how to calibrate one of our dual stream H2S analyzers. Before I hand it over to Al, who's going to take all of that away, I'm just going to give you a short introduction to who Envent is. We manufacture all of our analyzers here in-house in Calgary. We've got our M series, which is we have water, oxygen, carbon dioxide, all within that M series. We've also got our 330S, 331S H2S analyzers, so that's Class 1 Div 1 or Class 1 Div 2 option. We've got our Sulfur Sentry, which is a portable H2S analyzer as well. On top of that, we've got our gas chromatographs. So we've got our 131 and our 132, Class 1 Div 1 or Class 1 Div 2 option. And then we've also got our TFS, our tunable filter spectrometer. So if you're looking for WOBE index or to measure BTU, that would be a great option. Envent is also a rep for a Michelle instrument, so we can actually provide some of their analyzers for you for your applications. We've got their oxygen analyzer, water dew point, hydrocarbon dew point, and water content analyzers. On top of all of those different solutions, we will work with you for your application and create the right sample conditioning system for you. Make sure that it all works well properly. Once we put all of those together, we can add on the buildings, enclosures, and probe assemblies for that application. One-stop shop for you. Without further ado, I'm going to hand it over to Al, and we're going to get started. Thanks so much for joining.
Thank you very much for the introduction, Kendra. I'm Al Willett. I am Northern Alberta, BC Technical Sales for Envent. What we're going to be discussing with you today is the Dual Sensor H2S Analyzer, or Total Sulfur Analyzer, which we are going to get into a little bit later. So I want to bring to your attention hydrogen sulfide and some of the qualities of it and the importance of monitoring for it, which we're going to show you. Hydrogen sulfide, or H2S, is a natural occurring gas, and it can actually also be formed by decomposition of organic material in the absence of oxygen. So about a third of gas produced in Alberta contains this substance, the H2S, sour gas. It's colorless, heavier than air, extremely toxic. So in low concentrations you can smell it. It smells like rotten eggs, and it can irritate your mucous membranes, so the eyes, the mouth, throat. But in high concentrations, H2S can and likely will be fatal. So another characteristic of it is it's very corrosive, and in gas, water, air environments it is corrosive. So we got to protect people and we got to protect stuff from H2S, and that's why we want to monitor for it. Lead acetate tape. So this is a lead acetate tape analyzer. It just happens to be a dual sensor, which I'm going to get into a little bit, but a little bit about lead acetate tape first. So using lead acetate tape, there's a chemical reaction that takes place with H2S and lead acetate, and that chemical reaction turns the tape brown. In the presence of H2S, in certain quantities, it changes the rate at which the stain turns brown. So that's basically the theory behind the tape analyzer, is it monitors for the rate of change at which the stain is getting darker, or the rate at which the chemical reaction is taking place. So what happens is, and you can see that picture on the presentation you see, there's brown stains that are almost back to back. They're almost touching. Some of them in fact are, which is not a problem for the analyzer. So what we do is, in order to optimize tape life, is we want those stains nearly overlapping. We want them back to back, so that each individual stain that you see there was one analysis. So what the analyzer does, which oftentimes in the past people are familiar with tape analyzers that may have constantly been moving. This one doesn't constantly move. What the analyzer does is, at the beginning of every analysis, it stops the tape movement on white tape. I'm going to explain that a little bit later. Stops it on white tape, does a quick zero adjust. Every analysis it does this, and then it allows the tape to sit there on one spot and stain. And the rate of change, like I mentioned already, at which the stain gets darker, is what the analyzer is looking at to detect what your concentration limit is in your sample. So what happens, the tape, when it's sitting there and it's on white tape, we have a photodiode and a LED. The LED, a red LED, is shining light on the tape. The photodiode is detecting the amount of reflected light coming off the tape. So that reflected light on a white tape is at its maximum amount of light coming back to the photodiode. As the stain gets darker, your level of millivolts, which is the output of the photodiode, your level is dropping. Your millivolts drops as there's less and less reflected light coming on as your stain gets darker and darker. Hope that makes sense. So the darker the tape, or the darker the stain, the more chemical reaction that has taken place, the lower the millivolts is. Okay, next slide, please. All right, so our dual stream lead acetate tape analyzer. There's a couple pictures there for you on the presentation. The one on your left is the Class 1 Div 1, which is our 330S H2S analyzer, but we call it a 330S DS for dual sensor. Some people think dual stream, which can be applied that way as well. Excuse me. Grab a little bit of water. Okay, so the 330S DS, and the one on the right is a Class 1 Div 2, which is our 331S DS. Okay, and you can see, just like on my demonstration here, my demonstration analyzer here, we've got two sensors. So realistically, how this is working is, remember I showed you the tape staining that took place on an analyzer. What happens is, with a dual sensor, we see staining on both sides of the tape, because what we're doing is we're measuring on the front of the tape with one sensor, the back of the tape on the other sensor. Now, oftentimes people would think, well, what if you've got a dark stain on this one and it rolls up into this area, this visual area in the sample chamber? No concern. What happened, we have done many tests to prove that the stain does not go all the way through the tape. But even if there were some darkness, not quite as much reflected light coming back to the second sensor because of a stain on the back side of the tape, the analyzer does a zero adjust at the beginning of every analysis, so it compensates for that. So there are no concerns with that. So one other thing I want to note on a dual sensor, we're going to route our tape a little bit differently. This tape reel on the bottom is actually opposite of what it is on a single sensor. So there's a diagram here. I'm not going to go into a whole lot of detail because the detail I've offered in the past webinar, and that webinar was servicing an Envent H2S analyzer. So if you want to go back and view that, you can get a lot more detail on the H2S concept, the tape concept, I should say. All right, so the advantage we have here, we can measure two streams simultaneously, and you're only using one tape, one consumable product at a time, and only one set of electronics, so one motherboard. Everything takes place on the single motherboard. Okay, next slide. Thank you. So the range of samples that we can measure for H2S itself with a normal sample conditioning system, and our normal sample conditioning system is going to be a filter and a regulator, just to take care of some small issues, small particles in the gas. What we do is we can measure parts per billion up to about 100 parts per million. We can expand that, or we may not recommend it. It all depends on your application. All our analyzer systems are specified for our customers based on your application. So contact us if there's a need you have. We can fill that. So with our lead acetate tape analyzer, excuse me, we can also measure higher range. We can go from about 100 to 30% H2S measurement with our tape analyzer. And a lot of people would think, how can you do that? 30% H2S hits that tape, it's going to react instantaneously. The analyzer has no time to respond. Well, what we do is we add dilution. I'm going to get into dilution at the next step. The next slide will describe that in much more detail. Now, what we can do with our H2S analyzer is we can measure total sulfur with it. And in doing so, we have to add an oven. We're going to show you that in a little bit as well. Not in a whole lot of detail, because in the future, we're going to do a total sulfur webinar. So watch for that one. So with total sulfur, our range with a normal sample conditioning system is parts per billion up to 400 parts per million total sulfur. And then if we add a dilution system, what we're going to get into next, you can measure approximately 400 ppm up to about 30% total sulfurs. Next slide. Thank you. So, as you can see on the left, we have a dual sensor. Let me grab a prop. So you'll see this blue can on the picture. This is our dilution chamber. So how a dilution chamber works, let me pull this apart and then I'll describe that picture. So this is permeation tube inside the dilution chamber. So basically what happens is we flow a carrier. The carrier comes in one part of the permeation tube and goes out. Our carrier is going to be something that has no H2S in it. So your instrument air, clean, sweet, natural gas you can use. So what happens is if you look at that diagram on the right, we come into the bottom, there's two ports, we come into the bottom of this chamber with our high concentration H2S, and it's constantly flowing through. As it's flowing through, the carrier that's flowing through the center of our permeation tube, the permeation tube is allowing a small percentage of H2S into that carrier stream, which gets carried off to the analyzer. So once again, I've explained, if you have high concentration H2S, let me go back a little bit. This presentation, we talked a lot more about high concentration on a previous webinar already. So look for that one on our YouTube channel as well. That'll describe the permeation tube a little bit more and some options for measuring high range H2S. So the H2S analyzer typically will read, let's say 20 to 50 parts per million is kind of the maximum amount of H2S you want exposed directly to that lead acetate tape. Remember, it's a chemical reaction. That chemical reaction we need to ensure does not take place too fast. If it takes place too fast, it doesn't give the electronics enough time to find stability or find the linear portion of the curve, which I'm going to talk about in quite a good detail here right away. But so we actually balance these analyzers to ensure that they get a normal or a good length of analysis so that we can get a good reaction on the tape. Plus we don't want it too long because you don't want updates. It updates at the end of every analysis. You don't want updates in an hour or in half an hour. You want updates fairly repeatable and fairly quickly after you pull the sample out of the pipe. Thank you. So one thing we talked about is dilution, but we have applications where a customer's system has changed. Something's changed in their process, and they now are measuring higher than expected, and they do not have dilution. Well, you can see in that diagram, we actually have a dilution panel. We can provide you a dilution panel, so now you can reduce the amount of H2S exposure to the tape by throwing in a diluter. One thing I'll quickly mention, that permeation tube you saw in there, if you got really high H2S, that tube is going to be really short. If you've got low concentration but little higher than what we'd want to expose to that tape, you could have feet of that tubing inside that dilution chamber. So that's how we control how much gets to the analyzer or to the tape. So now I want to talk to you about the analyzer cycle, so the electronics behind it. What is the electronics doing? So I told you there's a sensor block. The sensor block has an LED shining light on the tape, and the photodiode is detecting the amount of reflected light. It's that process that I'm going to discuss right now. So if you look at this, the axes that we have, we've got 0 to 1,000. That's your millivolts. So remember I said that photodiode is outputting a millivolt signal to the electronics. This is the millivolts we're talking about. So remember, it starts out with maximum amount of reflected light, which is our maximum volt or millivolts at the 0 point, at the point at which the analysis starts. Then as the stain gets darker, as the chemical reaction takes place, your millivolts starts to drop off because you got less and less reflected light going back to that photodiode. Okay, so that's the concept we got going here. The bottom axis is our time. Okay, so if you look at that, point number 1 with the circle in there in the chart, point number 1 at the bottom on the left, that is the end of the current analysis. So at the end of the analysis, what happens is we move to point 1 up to 2, and that's your tape movement. So your tape starts to advance and stop so that you're looking at white tape. We want to all the time guarantee the beginning of an analysis is a fresh piece of tape so that we can get a chemical reaction to take place from basically, let's call it ground zero. But our ground zero on this analyzer is in millivolts. So When we do a tape advance and we look at white tape, the first thing we do is quick zero adjust to compensate for any, maybe some dark staining or some staining or some whatever changes in the color of the tape. We do a zero adjust. So that zero adjust takes place, and then the analysis starts to take place. So remember, we're just sitting there staring at the tape. We're looking at the tape, monitoring how quickly it is getting dark. So between points 2 and 3, that's what's taking place. The millivolts is slowly dropping. Now what happens is the analyzer sitting there watching our millivolts. If we get to a point where we are at a 100 millivolt drop, so one thing I should mention is this chart is very specific, call it laboratory. We're saying that the analyzer zeroed at 1,000 millivolts. At 1,000 millivolts, it's going to be plus or minus 100, so don't take this 1,000 millivolts as gospel. It's not necessarily going to be 1,000 millivolts. It could be 900 up to about 1,100. Anywhere in there is very normal. So let's use 1,000 for this example. So it starts up at 1,000 millivolts, starts to slowly stain's getting darker and darker. Now what we're watching for, what the electronics is watching for, is a 100 millivolt drop. So it went from 1,000, and like on this chart, you see at the point where it hits 900 millivolts, the 100 millivolt drop that it's looking for. Now what it does is it says, okay, I am now in my most linear portion of my curve, most linear portion of my reaction, the chemical reaction on the tape. So between points 3 and 4 now, we're in that linear portion, so where we have uniform light absorption on the tape, or off of the tape, absorption onto the photodiode. So between points 3 and 4, now what the device does at point 3, don't let this confuse you too much, I'm going to talk about it again in the next slide, but at point 3 what it does is it says, how long did I take to get from my 1,000, or how long did I take to get a 100 millivolt drop? It takes that period of time. In the example you can see that it's 600. So how long did it take to get to 100 millivolt drop? It took 600 seconds. The math does this every single time. However long it took to get to 100 millivolt drop, it takes 20% of that. It adds that 20% onto the total analysis length, or onto the period of time that it took to get there. It adds 20%, or divides that number by 5, and it runs that period of time. So as you can see, the 600 seconds that it took to get to 100 millivolt drop in this example, that if you take 20% of that, you've got 120 seconds. So the analyzer is going to run up to 720 seconds. At the end of that 720 seconds, it runs its calculation to tell you what the concentration is based on that portion of the curve, because we consider that the most linear portion of the curve. So at the end of that analysis, at point number 4, it goes back to point number 1, does a tape advance, gets white tape in there, allows it to stain, waits for 100 millivolt drop again, does the same thing. Okay, so it just keeps repeating that process. So that's how that works. Next slide. Thank you. So we're not talking about a single stream. That's what occurs on each individual single stream in our dual stream or dual sensor H2S analyzer. So there's going to be a little bit of, they're not going to be obviously hitting a 100 millivolt drop at the same time. So this is why this needs to be described to you. Here's what happens. Before these things even leave the factory, they're balanced. We balance these things so that we get a good tape life, but also allow enough time for this linear portion of the curve to occur. Okay, so there's a balance there that takes place with each H2S analyzer even before it leaves the factory. Because what we're going to do is we're going to ask you, what are your alarm points? Where do you want to alarm at? Where are you normally operating at? Those kind of things is what the guys in the factory use to determine how long we want your analysis to run, also what size of aperture they'll put in there. If you don't know what an aperture is, the previous webinar we spoke about, it's on there. We describe that in great detail and show you examples and everything, so feel free to go back to our YouTube channel and watch those so you can get a little better understanding of what's behind this. So with a dual sensor, I'm going to try to use my hands here to describe in the best detail possible. You've got two sensors now spitting out approximately 1,000 millivolts each. Okay, so the tape, one tape, so the tape doesn't advance. Now we're at point number 1 on both. Or sorry, we're at point number 2 on both. Tape advances at point 1, tape is advanced, now we have white tape in front of the photodiode. Okay, so we're getting our maximum amount of light reflected off that tape. Once again, 1,000 plus or minus 100. So now here's both of them. Let's just say they're at 1,000. So we've got our both sensors, two separate sensors measuring reflected light. One stream is likely going to stain different than the second stream. So, in fact, I would guarantee it. So you've got two streams measuring H2S, two separate streams coming in. Each of them is balanced, so we get approximately the same length of time. About 600 seconds is very typical for an analysis length. And then we get into that linear portion of the curve. So here's what happens though. If you have one stream that happens to go off spec, for example, so it's going to go sour, my hands are a representation of the millivolts. So let's say you've got this one stream that goes sour a little faster, okay? So we're at 1,000 at 0. Now we're staining, our millivolts is dropping, but this one all of a sudden starts to drop off because you've got higher concentration H2S coming in, higher than expected. So the millivolt signal is dropping. This one hits 100 millivolt drop. This stream itself will actually do that quick calculation, get 20% of that period of time it took to get there. It adds that on, and it allows the analyzer to continue to monitor for that extra period of time. So now we're in that linear portion of the curve, spits out your concentration value to your display. So now you've got this stream that has updated a number, but this one's not there yet. What happens is this one will continue to stain. It's good, because while we're waiting for this one might go crazy. It could get really sour and drop way off. Therefore, you want to know about that. So it'll continue to monitor this stream even though it's updated its number. Second stream now takes its time, but it gets down to 100 millivolt drop. So that 100, once it hits, it does the exact same thing that this stream did, just like a single stream analyzer would do. It does that calculation, gets 20% of that period of time it took to get there, adds that on, goes till that end of time, that period of time that it calculated. It uses that linear portion of the curve, throws a calculation, it gets its concentration. Now this one's updated to the device. This one now updates. Now you're at 0.4 on both of them. So what happens is this one updated, waited, this one updated, then when this one updates again, because remember this one was still running, right? Because you could have a change in concentration. Typically it wouldn't occur that quickly, but it can. So this one updates again. So when you're watching your local display and you happen to see one of your dual sensor streams update, you're going to see it continue to run until the second one updates, and then you'll see that first one update again. Can create some confusion, but that is what is occurring. It's updating again because there could have been a change while it's finished its update, could have been a change in concentration. So you'll typically see when it updates that second time at the end of the entire analysis, you're typically going to see it's going to be very close to what it was before. So quickly, yeah, that's about it. Hopefully that makes sense to everybody. So one thing we talked about earlier is the fact that we're doing H2S. Typically we can do H2S. Yeah, Kendra, why don't we push that in here? You can see on the display as well. Thank you, Kendra. You can see on the display as well, what we can do is total sulfur. So we offer the Dual Sensor H2S analyzer to measure two H2S streams, but what we can actually do is have one of those H2S streams be a total sulfur stream. We're going to run through some examples of applications where you can use this. But what happens here is we take, remember I told you it's an H2S analyzer. That's all it is. It's an H2S analyzer, and you can see this is a dual sensor as well. So two sensors, one tape. But we have this oven down here. In order to convert, or in order to measure H2S on this tape, remember I told you that it is interference free. So being interference free, if you have carbonyl sulfide, for example, it's not going to react on that tape, even though it's a sulfur compound. So what we do is we convert all sulfur compounds into H2S to be measured as H2S on the tape, because it does react on the tape. And therefore our output for that stream, if it happened to be total sulfurs, which I'm going to explain a little bit, is going to be measured as H2S, but the output's going to be a total sulfur number. Hope that makes sense. But here's what we do. Here's the process. So we take our stream number 2, for example. The stream number 1, in this actual build, this is a build going out to the field. Stream number 1 is our standard sample conditioning system. So it has a filter, regulator, and then it goes in through the flow meter and gets measured into the sample chamber. There's more detail that takes place. There's a humidifier in there, etc. Past webinar describes that in great detail. So This stream, though, this is our total sulfur stream. So we filter and regulate it, but we also have hydrogen coming in. So what we're doing is we're taking our sample, let's just call it our H2S stream. We're taking our sample, we're mixing it with hydrogen. Okay, so we mix that with hydrogen, we heat it up to about 900 to 1,000 degrees Celsius, and then a chemical reaction takes place inside the oven. I'll describe the oven in a little bit of detail next slide. But so we've got our H2S and our total sulfur, H2S and our sulfur compounds entering this oven at about 900 or 1,000 degrees Celsius. I apologize. H2S and hydrogen are, here we go again. H2S and total sulfur compounds, your sample flowing in, combined with hydrogen at 900 to 1,000 degrees Celsius, converts all your sulfur compounds to H2S. So now what you have is you have this larger amount of H2S leaving, if you have total sulfurs in your sample, leaving the oven, going up and being measured as H2S. I hope that makes sense. So realistically, all we're doing is we're mixing hydrogen with your sample, heating it, and it takes the H2S reading, because everything's been converted to H2S, and takes it into your total sulfur sample now, or total sulfur measurement. Now, one thing I want you to understand, and this can be a little bit confusing at times, if you have H2S already in there, and you have total sulfurs, when you get your final number, that is your H2S plus your total sulfurs combined to make a larger amount of H2S. Okay, I'm going to talk about that in a little bit, because what's important is that people realize that if you're measuring H2S, let's say you're measuring in the exact same stream. So your T off here, you're going into the same stream. You're measuring your H2S here, and you're measuring your total sulfur here. If you ever had a case where your total sulfur number was lower than your H2S, that's near to impossible. That is impossible, because you already have that H2S in the stream. It should at least measure the same. You should at least see H2S, but what can occur inside here, I'm not going to go into a whole lot of detail, but you have a glass tube. I'm going to grab one here, for example. You've got these quartz tubes that are sitting inside here that your stream is flowing to and getting heated. Now, this is a good one. This is clear. This is how they start out brand new. This is one that's coked. What can happen is when you heat hydrocarbons, they'll coke. So you'll see the difference. Now, what can happen when you coke up a tube is one of two things. You can eventually block it off and you get no flow. But what happens is with this coking, you'll actually absorb a little bit of your H2S and your sulfur compounds into that. So what can actually occur is you'll have H2S reading coming in, and you'd expect to at least have the same amount of H2S coming through this tube, but you'll actually be lower, like I already explained. Your H2S and H2S should be the same. If it isn't, if you have sulfur compounds in there, of course your total sulfur is going to be higher than your H2S, because it's your H2S plus the sulfur compounds. Hope that makes sense. A little troubleshooting for you to understand. But we're going to get into that in a lot more detail in a future webinar, of course, when we talk about the total sulfur analyzer. Okay, next slide. So the breakdown of this. If you look at that slide, you can see the quartz tube where it's labeled quartz tube sticking out of each end. I'm going to hold this tube. I'm going to use the one that's all coked, for example, so you can see it better. If you look over here, this quartz tube sits in here. You don't actually see these ends. All you see is these little ends. Therefore, it's described in there that typically just the small ends are visible. This is, as I step away, this is what's inside this container. This is sitting at 1,000 degrees possibly. And your tube goes in like this, and all you see is the ends. You just see the ends sticking out. Okay, I wanted to describe that so there's no confusion on the diagram. So we come in, each one of these has a flame arrestor. We come in with our H2S and our hydrogen, go through the furnace, reaction takes place, converts all your sulfurs to H2S, and you have H2S leaving, going up to the analyzer to be measured as H2S. And then the brains in here, behind here, knows what stream is the total sulfur, spits out a total sulfur number. And that's it for that one. Thanks, Kendra. We're going to talk about the calibration here. when we calibrate this device, first thing we always suggest is hit that bypass button, or you're going to have to maybe bypass it in your DCS. However you got to bypass it so that when we run CalGas in here, likely causing an alarm, it doesn't affect your process. So we've bypassed it. If you want to know more detail, once again, that past webinar describes all that in much greater detail. You're going to turn your calibration gas on. Now, what thing we can do, what Envent recommends for calibration gas is H2S and carbonyl sulfide in the same CalGas bottle. Because if you're running H2S and total sulfur, in this case, you're going to have the ability to have both of them combined into one. Now, in the case where, let's say you had H2S and another H2S stream, because you got you may have two different concentrations of H2S, you're going to need two separate calibration bottles. But in this case, we could put our H2S and our sulfides in one calibration bottle. So I'm going to use the example of, say, 10 ppm H2S and 190 parts per million of sulfur compounds. Envent recommends carbonyl sulfide. So that's what you'll see out there typically is a carbonyl sulfide H2S in a nitrogen background for your CalGas. But we can run them simultaneously because we've got two separate portions of the analyzer that we're using doing two separate calculations. So you can run it at the same time. So what we'll do is we'll tee our cal bottle off typically. We'll go into both streams at the same time and we'll allow the analyzer to stabilize on that. So you've got 10 ppm H2S, you can simply adjust your gain, calibrate that to 10 ppm. That one's easy. That's just like a normal H2S calibration like it would if you were H2S and H2S. But now the total sulfur, this can be a little bit confusing at times. What is the total sulfur? Remember, we're coming in here with H2S and carbonyl sulfide. Converting the carbonyl sulfide or our sulfur compounds get converted to H2S. So now we have H2S and H2S. Okay, so you have to add them together. They go off and they get measured as H2S. Output is a total sulfur number. So one thing I'd like you to do is look at that the calculation really quick. In order to adjust a gain, what you basically do is you take your CalGas concentration. So let's use H2S for example. Take your CalGas concentration, 10 ppm. You take your actual reading, what it's reading now, let's say it's 8, let's say it's 9 or 8.9, doesn't matter. So you multiply your gas concentration by your current reading, you divide, I apologize, you take your CalGas concentration, you divide that by your current reading, you multiply the current gain that's entered into the device, and that gives you your new gain. It's cross multiplication. But keep in mind, when we're talking about total sulfur, in order to adjust that, what you have to do is you have to take the total sulfurs. So if you've got 10 ppm H2S and 190 ppm carbonyl sulfide, you're going to want to add those together to make 200. So now you've got 200 total sulfurs. Remember, H2S and your sulfurs are added to each other after the reaction takes place. So just keep that in mind, that you're always looking at your CalGas bottle. If you've got H2S in there and you're converting your sulfurs, you've got to add that amount of H2S to your total to make your total sulfur. Then you're going to return both streams back to normal stream, back into service, and then you're going to allow the analyzer enough time to come down, take a new analysis, and make sure that it's back into its normal operating range. Then you can take off your bypass or take the bypass off in the DCS or the RTU, either way. Okay, some applications. So some applications for this, I'm sure many of you out there right now have already thought of some applications that you could apply to this. When I first saw this concept, it was being introduced years back, and I was in the pipeline industry. We have co-located facilities, so two facilities from two different producers coming in, and then we go into a common header off to the pipeline. One thing, when I first saw this, I thought, wow, cost savings. What a great concept to be able to measure two streams at the same time, because these co-located facilities are in the same yard. So instead of buying one analyzer for this metering facility, one analyzer for this metering facility, we could buy one and just run a sample line to the other one. And therefore you're measuring both simultaneously. Different outputs, your outputs can go different locations. I thought it was revolutionary. In fact, I know it is now. So One thing that you can use this is for like plant inlet outlet, like you can see on the display. Sulfur recovery units, inlet outlet. A scavenger, pipeline blending, like I just described, wastewater treatment, biogas and landfill. So biogas and landfill, you're going to typically be using this device to measure one stream, but you're going to want to know your H2S and your total sulfurs. Same as the acid gas injection, H2S and total sulfur system. It's very similar to this. I like the sour wellhead idea as well for blending. So what we can do is we can have multiple sour wellheads coming to a common header. You could use not necessarily this case, this is total sulfur, but let's look at this and just imagine this is H2S and H2S. What you can do is you can have your one stream, let's call it the constant measurement stream, being measured, and that would be your common header. So you're looking at your total amount of H2S coming from all your wells. And the other stream, it could be measuring one or multiple, because we can do stream switching. So you can stream switch between wells to sit there and watch to make sure you can tell which stream goes sour. And you'll see the response basically on your common header as well. So if this becomes elevated outside of tolerance, you can tell which well is the culprit. I like that idea. Next slide. All right, so that we're complete here. We've described the H2S Total Sulfur Analyzer a little bit. Watch for a Total Sulfur Analyzer webinar coming soon. And we're also going to, what we have in the queue, we're also going to talk about the TFS in a little bit more detail. I explained that a little bit earlier, where we could use other devices to measure the higher concentrations. Well, this TFS is one of those we could apply to your application. So we've got TFS, total sulfur, coming. We've got other ones in the queue. We haven't built them yet, but they're coming. So one thing I want you to do is complete the survey. You're going to see a survey there at the end of this. We'd like you to complete that, because one thing we want to know is, what do you guys want? What do you guys want to see in the future? What webinars would you like to see coming up? So we can do that if we get your feedback on that. And also, at the end of this presentation, very soon, we're going to sit here and we're going to monitor the question answer session or section of this webinar. So we'll be here for a little bit to answer your questions. So once again, thank you very much for joining us. Have yourself a great day.